Hi everybody, this is going to be a real short video and it's meant as a follow-up to the thought experiment on relativity that I had you do. This is for those who either are remote learning or who maybe weren't able to have part 2 ready in time for us to talk about it as a class, and so after you have done part 2 and part 3 you can go back and take a look at this and kind of get what everybody else was getting. We looked at a number of scenarios, and I asked you some questions regarding what you think would happen, and then I had you back that up with your own justification. So we're going to go through these, and while the answers that I'm going to show you are not the only possible right answers, because I don't know everything, these are going to be some of either the more popularly chosen ones or ones that actually are borne out through experimentation. So the first scenario, you were put in an elevator and you were put on a weighing scale and you were asked what would happen at a variety of different situations if the elevator was in motion. If you're standing on just a normal weight scale, then it's showing an expression of the force of attraction between you and the Earth. In other words, it is showing force due to gravity. That's depending on your mass. It's also depending on acceleration due to Earth's gravity, which if you took physics, that's 9.8 meters per second per second. So if you're standing still, the gravitational force is acting downward on you. The normal force is acting up. That's that force that opposes anything that's pushing on a on a perpendicular surface. If the elevator is moving downward, then you have a lessening of that force pushing up. And so since you have less of a force pushing up through the floor, you're going to have a little bit less force coming down. Or it could be explained that you now are being put, I don't know really exactly how to explain this, to be totally honest with you. There's not as much getting in the way of gravity having its way with you. And so you would measure lighter on the scale than you normally would. Just the opposite of that if your elevator was moving up, because in addition to the normal force coming up from you just touching the scale, there's an increased force of acceleration from the elevator moving upward. And then finally, the very last one on that first scenario is, what if the elevator cable was cut and it just started falling? Well, at that point, you would not have any apparent weight. You would, for all effects to you, be weightless. What's actually happening is that both you and the elevator and the scale are in a state of what's called free fall. And if you remember from physics, free fall is when the only force acting on you is gravity. There is no normal force, there is no air resistance or any other forces that would be affecting your motion. And that leads us a little bit into talking about scenarios 2 and 3. In scenario 2, we talked about two individuals that jump into a bottomless pit and then begin falling. From the outside, it would appear to you, standing up at the edge, that they would begin moving downward increasingly faster for as long as you could see them, toward the center of gravity of the Earth, I'm presuming they're standing on. However, to each other, as they're both falling, they're falling at the same rate because they're both being accelerated by the same gravity. And so they would appear to each other to stay more or less relatively motionless. One is not going to start falling farther or faster than the other. They're going to fall at the same rate, so to each other it's almost going to be like they're not falling at all. And then you were asked if they had a basketball and they wanted to pass the basketball to each other, where they should aim it in order for the other person to catch it. And while here, just if we're not falling, if I wanted to pass a basketball to you a long way away, I might have a tendency to sort of angle it upward to where it would kind of follow an arc path, because it would be, once it's in free fall, it's going to be accelerating downward because of gravity. But in this case, the individuals themselves and the ball are all experiencing that free fall, so they're all already falling at the same rate. So in order to get the fall to each other, you are going to aim for the other person straight on and push the ball in their direction. And it doesn't have to even be a fast push, because since the ball is already falling, it will continue falling at the same rate as you if there's no air resistance. So I could just give it a light push, and it would look like it's floating straight to you. Whereas if I aim slightly above your head, you will have already fallen by the time it gets over there. Or if I aim below you, then the ball will also fall, and you're never going to catch it. And that leads into scenario 3, where we had the lady who was locked in a room with no reference to the outside, and all she knew is that she was weightless. Got a lot of interesting answers on this one. Now, if we discount that she's probably not having an out-of-body experience, she's probably not a ghost, she has not been abducted by, well, I don't think she's been abducted by aliens, and she's not dreaming, then there's two possible scenarios that present themselves. One, she could be out in space, either in orbit around a planet or in the space between planets, interplanetary space, in which case she would be weightless. And so would all of her belongings, her purse, her keys, her cricket bat. It would all be free to just sort of float. Now, the other possibility would be, kind of like the two individuals in the bottomless pit, she could be in a room that is falling. And if it's falling, she is falling, and everything inside of it is falling all at the same rate. And so to her, from her point of view, she wouldn't be moving. This led us to an interesting conversation this morning about, well, how do you know if you're falling? And that has to do with the semicircular canals inside of your inner ear that detect changes in the orientation of your head, and there's little nerves in there hooked up to fluid and hairs that kind of let you know in all three dimensions what direction your head's pointing in. And if you start falling, then they will also sense that. Someone who is in a free fall situation, or someone who is in weightlessness, basically their brain is sending them the message constantly, hey, you're falling, you're falling, you're falling, you're falling, you're falling. And so for a lot of people, that's one of the worst things about first getting into a weightlessness situation, is their brain is telling them to panic, but they're not seeing anything to panic about. And so it's very often for people to get nausea, throw up, and feel really rotten because of weightlessness. NASA uses a special airplane that goes up in the air and then starts diving at very high speeds to train astronauts in weightlessness. They've nicknamed it the Vomit Comet. If you've seen the movie Apollo 13, a lot of the scenes where they appear to be weightless were filmed inside of an airplane like that was actually in free fall. Kind of a cool thing. And the final scenario had to do with two people standing in a spaceship that's orbiting around a planet. And if they're orbiting around a planet, that's just a special case of free fall. Because if I am in orbit around a planetary body, that means I'm falling toward it, but I'm also have a forward velocity that causes me to sort of miss it as I fall. So it's like something in orbit is constantly falling around the body it's orbiting. It just never hits. And so if you imagine two people that are in a spaceship, it's going to be very similar to what happened with the two that were in the bottomless pit. They can pass a basketball to each other, and although the spaceship will move and change its orientation, the basketball is also falling and being accelerated due to gravity, so it will also change its position accordingly. So to the folks on the inside, it will look as though it's flying straight from person to person. Now, what's interesting about this is when you bring in the laser pointer. Up until now, everything we've been talking about being affected by gravity has mass. It's made up of matter, atoms, molecules. Light, on the other hand, does not have mass. Light is a form of energy. It's a form of electromagnetic radiation. And so light having no mass of its own, you would have to wonder, would light be affected by gravity? Would light fall toward a planet, or would it continue on straight? Now, your brain, based on what you know about light, tells you that if it's aimed in a straight line, it's going to continue in a straight line. And if the spaceship is out of position, then it's going to miss the target you aim it at, because the target will have moved. Now, you have to kind of imagine it's very slow-moving light, so we could actually perceive this. But that's not what happens at all. What happens is that the light is also bent toward the planet. In effect, the light is falling. Now, according to Isaac Newton, that shouldn't be a thing, because he defined gravity as a property of matter, and he showed in his law of universal gravitation that if you have two bodies with mass, then they are going to have some form of gravitational attraction between them, and it's dependent on their mass, but it's especially dependent on the distance in between. So according to Newton, light shouldn't fall, yet it does. And so there we have to actually have a slightly different paradigm for how we think about how gravity works. So enter this fellow right here, Isaac Newton. In the early 19-teens, he started doing what you were doing for this activity. He started just having thought experiments. And he theorized that, well, what if Newton's model was not entirely accurate? It served us very well for a very long time, describing interactions of things falling on planet Earth, but what if you get to truly massive, truly high sources of gravity? And so he envisioned, what if gravity is not a property of matter? What if gravity is a property of the universe? And that in all of space and in all of time, it has basically a field of gravity. And objects that have mass tend to warp or distort that field and kind of change the shape into a curve around it. For something like you and me floating around in space, that would not have a lot of change on the curvature of space, but for something like a planet or a star or a black hole, where you have massive, massive dense matter with lots and lots of mass, then it's going to make very substantial curves in what he called space-time. So what's going to happen is things are going to be caught in that curve due to a massive body, and it's going to change their direction, including something like light, because it's not the matter with the gravity, it's the space. And when the space is bent, that means anything passing through that space also has to get bent. This was tested a few years after he made the theory during a total solar eclipse. Astronomers mapped out very carefully the positions of stars, and then if Einstein's theory was correct, then the path of light from those stars should get bent and distorted as it passes close to the sun, which you normally can't see because the sun is so bright. But if you wait till a total solar eclipse, then you can actually check and see stars that are very close to where the sun appears to be in the sky to see if there is any distortion, to see if they're out of place. And sure enough, I think it was two different astronomers working semi-independently made their own independent observations that helped to lend support to Einstein's theory of general relativity. We'll talk some more about general relativity and some more implications it has for space exploration and for the creation and evolution of the universe at a future time. Thanks for watching.